Okay, it's an important concept. So we got the basic idea. Okay, so now we have the diffraction maxima at the base. Okay, not diffraction. The bending moment maxima at the base. Okay, but the maxima diffraction is at the tip. Okay, so after we have the 2 times integration and provide also the boundary condition, and we finally got this equation. But this equation, we show up the diffraction is not the strain, the diffraction. So the diffraction will have the maximum at the tip instead of at the base. When you put the value into L here, you got the maxima at the tip. Okay, so at the tip you got a maxima diffraction, but at the tip the strain is the smallest one. Okay, because the curvature is the smallest one at the tip. Can you understand? Okay. And also, from this equation, you take the first derivative, you got the angle. That means if you derivative this one, you got the dy dx. That means the slope, okay, of the curve. The slope of the curve means the angle of the curve. Yeah, because if the angle is small, the dy dx equal to tangent theta, right? So when the theta is small, the tangent theta similar to theta. So we can consider theta equal to dy ds squared, dy dx. Okay, so you have this curve and derive once. You got the angle of the curve at a different position. Okay, that's the equation. And you put it into the tip diffraction. You got the maximum diffraction like this, and also the maximum angle at the tip is like this. Okay, and if we consider the cantilever beam as a spring, okay, so the spring, when you apply some kind of force, so the spring will give a certain kind of a deflection, or the different extension, okay, the elongation. So we can using the equation to replace the parameter. For example, like the spring equation will be the F equal to K times X. X means the displacement of the spring. Okay, here the displacement of the spring will be, you can use the original equation. It will be easier. The diffraction, y, yeah, this one. The diffraction X here will be the Y, the displacement of the spring. F equal to Kx, the X is exactly the Y here, the diffraction of the beam. And the F will be here. So if you don't consider moment from the beam, using only this part, okay, and also actually using this equation, you consider the tip diffraction YL equal to F times the spring constant. So the rest of them will become spring constant, K. So K will be equal to L3 over EI3, L cubic over EI3. Spring constant K, sorry, K times diffraction. So the reverse value, L3, 3 times EI over L3 here. So this part will be the spring constant. Do you understand? Okay, let me write it down. So this is the diffraction at the tip, okay? So if we consider okay, so if we consider this like a spring, okay, so for spring equal to spring constant times the displacement, right? Delta S displacement. So the force is here, so this part will be the K. So this will be the displacement. So you can replace K equal to this one in the cantilever system. It's Hooke's law, yeah. So the deflection in the cantilever can be considered as the elongation of the spring. Understand? 弹簧的伸长缩短这个部分呢，可以看成悬背梁的弯折。悬背梁的弯折的量，可以看成像弹簧伸长缩短的量是一样的。所以这个弹簧伸长缩短呢，可以用这个东西去取代。所以剩下这个部分呢，就变成了弹簧常数。所以可以把悬背梁看成一个弹簧。OK， 所以你给悬背梁一个力量，它会有偏折。就力量跟偏折的关系的比值就是它的弹簧常数，就这样的。OK， so we can consider cantilever as a spring. Okay, so for a spring system, you have a spring over the displacement. You got a spring constant. The ratio between the force and the displacement will be the spring constant. That's it. So the spring constant will be this part. Reverse the value. Okay. So, so every time we'll talk about a spring by using cantilever, so we're using this equation. So the interesting thing is for higher natural frequency, you need to increase the spring constant. That means you need to increase this value. That means you need to have a shorter beam because it's a cubit on the bottom. And also you need to have a larger Young's modulus and a larger momentum of inertia in order to get a higher spring constant from this equation. Yeah, you want to increase the spring constant, make a very strong spring for cantilever. You need to increase the Young's modulus, increase the momentum inertia, but reduce the length of the beam using shorter beam. Okay, and vice versa. So if you have a small spring constant, very soft spring, you need to increase the length. Yeah, and also it's very easy to increase the length because it's a length cubic. So if you increase the length by twice of the length, and the spring constant will be reduced by 8 times. It's quite efficient. Okay, quite effective. Okay, when compared to changing the Young's modulus or momentum inertia. Okay. Okay, so you can also replace the momentum inertia into the structure of the beam, the thickness of the beam, and also the width of the beam here. Okay, you got the final results here. Okay, yeah, it's a very useful equation for cantilever beam to consider cantilever beam as a spring. The spring constant is very useful for your design later on. Okay. So now in the dynamic, the kinetic equation, we have the first term, the inertial term. This is the third term, the spring constant term. Now we will consider the second term, the damping term. For the damping term in the current system, because our proof mass will go up and down, right? So that's the only motion we have. So we'll consider one damping will come into the system is we call the squeeze fin damping. The squeeze fin damping, that means we have the plate moving up and down, and if the plate is close to a bottom surface, so the air underneath will be pushed away from the small channel to outward. So in this case, the movement of the fluid will give a lot of friction onto the surface of the plate. So this process we call the squeeze fin damping. So according to very complex fluid mechanics calculation, you can find out actually the force when you push down the plate close to the bottom surface to squeeze out the air from the bottom, you can find out that the force will be proportional to several things. The first one is the speed you push down. So if you push down the speed faster, you get a larger force because you want to move out the air on the bottom faster. In that case, they will generate a lot of the velocity difference for the center part and the border part. So this also gives a lot of shear force. So higher speed, you have a larger shear force. You have a larger shear force, give it a lot of resistance force when you push down the plate. Okay, so the plate force, the resistance force will be proportional to the speed of you pushing down the plate, and also will be proportional to the distance, the inversely proportional to the distance. If you have a smaller distance here, okay, and the force will be larger, so it's also sensitive to the distance d here. For smaller distance, that means when you push it down, the air will go out from a very small channel. Smaller channel give it a lot of shear force because the velocity variation, the gradient of velocity will be higher. Okay, the velocity variation will be higher, so give it a larger force, the shear force. So the force for pushing down will be proportional to the speed and also the distance between the plate and the bottom surface. Okay. And also some parameter k over here. The k equal to the size of the represent the size of the disk. Currently, we are thinking by using a circular type of a disk, okay, to simulate. But in the design, we are using a square type. It's a little bit different, but we can use this to estimate, okay, give an estimation of what kind of damping force we can have here. So the k, the parameter k here is proportional to the size of the plate. So you have a larger size, you also have a larger force, okay, because you need to push out the air from the bottom for a longer distance if you have a larger plate, okay. And also the viscosity also give a factor. So if the air underneath is more viscous, if you put it as a water, it's not air, will become even more difficult to squeeze out the solution, okay. So yeah, it depends on several parameters. So this force can be considered as a first order force. That means this force is proportional to the speed of the movement of the plate. This is considered as a damping. Okay. So the damping coefficient will be the combination of Kb over D3, the total things. So in your homework, you were asked to calculate the damping of the system. Okay, and to see if we have this kind of damping, the whole system can be in which kind of the dynamic situation, is under damping, over damping, or critical damping situation. Okay, yeah, because the damping coefficient, the situation of the under damping, critical damping or over damping situation will depend on the B square over minus 4 km. So if we have a damping coefficient equal to 4 times the spring constant and also the mass, the damping will be critical damping, right? The system will be critical damped. However, in most of the cases, it's not. Yeah, if you have a far away of the plate from the surface, usually the damping is pretty small. So you always got the under damping situation. That means after the stimulation of the plate, the plate will keep vibrating for a very long time until it stops. That's the usual case we see. Okay? Okay, this is squeeze damping part. Then we will consider strain, okay? Now we have the curvature. The maximum curvature occur at the end, the base, okay, of the beam. Now we will consider, we want to transfer the curve into the strain on the beam. Okay, for the strain on the beam, we consider here, because it's not a joint here. So when we have a curvature like this, we have a large curvature here, smaller curvature here. So it's bending more here, bending less here. So you have a large bending here. That means if we consider the material on the top, the material will be expanded much more, right? And on the bottom of this structure, the material will be compressed, right? So consider we have a curvature like this. The top material will be extended, the bottom material will be compressed, right? So across the beam, somewhere, because the top is a tension, is a extension, the bottom is compression. So somewhere between the top and the bottom, there will be a surface without any extension or compression, right? So this surface we call the neutral surface. No any distortion, the surface. Okay, no strain at the center. So when you draw the strain, the displacement across this cross section, because on top is tension, so I would draw like this. On the bottom is compression, so I draw like this. So the strain across this cross section will look like there will be a neutral surface. At the center. That means at the neutral surface, there won't be any strain, no displacement, no distortion here. On the top, you have an extension, so material becomes longer. On the bottom, you have contraction, the material becomes shorter. Okay, so you got a positive strain and a negative strain on the top and the bottom surface. Okay, so now we consider we will put a sensor at the base, right? And also at the base, you have a different position to put your sensor. You can put it either at the center, at the top surface, or the bottom surface. Okay? Now again, we have a 3 choices. 1, 2, 3. Okay. The first one, you got a position at the base. It's okay. Yeah, everybody understand why. Because we have a larger curvature here. Now we will consider at the base, which position you will put your sensor. Top surface, center, bottom surface. Which one will be your choice? Again. Okay, have you decided yet? Okay, now we will see the final results. If you think the first position is the correct position, please raise your hand. Number 1, please raise your hand. You think? Okay, good. 1, 2, 3, 4, 5, 6, 7. Only 7? Okay. Center 1? No? Bottom 1? Okay, the other 1, 2, 3, 4, 5, 6, 7, 8. Okay, you do this second time. Okay. 2, 3 together. Okay, good. So we've got 10 more people on the bottom. Okay. Yeah, please put down your hand. Okay. So the answer is we can put the sensor either on the top or on the bottom, as long as they give you large extension or compression. We need a large displacement to give a large signal. Remember. So either on the top or the bottom is okay. Depends on the sensor type. Some sensor is more sensitive to the extension. Some is more sensitive to the compression. Okay, depends on your sensor. But either one is okay. Okay, but not the center one. Okay, remember. Because the center one does not give any displacement, no distortion, no length change. That means no signal. Okay, so don't put your sensor at the center. Okay. I think most people got the idea. So for the cantilever beam, for piezoresistive type sensor, usually we will put the sensor at the base and also at the top, either top or bottom surface. Okay, depends on your needs. So if we put it on the top, so the strain will be the highest. So strain will be equal to this one. The strain actually equal to the curvature, the distance over the curvature, and finally is A over 2 zo. Though 1 over though is the curvature. A means the distance from the neutral surface to the most outside surface, the distance. This means the half of the thickness, okay, of the beam. A over 2. So actually, the maxima will be appear on the top or bottom surface. So the maximum strain will be like this. So now we already have a 1 over though as your spring constant here. So the maxima curvature will be at the end, at the base, okay, when x equal to 0. So this also gives the maxima curvature. So you put in the maxima curvature back into here. So you got the position will be at the base and also at the ulterior surface. This is the part you need to put your sensor. So finally, you got the epsilon maxima. The maxima strength will appear on the top surface at the base of the cantilever beam. So that's the final results of your maxima strength coming here. Okay, and that's the end of this one. Okay, so let me finish the other part because the other part is also important. Okay, so now we can compare a little bit our original map. The signal process. Now we almost halfway to the center part. So consider we have cantilever beam. You have a force here. You have a bending moment. Bending moment give you displacement, and also the strength will be found out at the base, and also the ulterior surface. So you got the strength here. Now we are going to transfer the strength into the resistance difference in order for the final measurement. Okay, so I hope you did not get lost. Okay, so every time when you get lost, you come back to this map. So think of where you are. Okay.